we have the next talk by Chouaf, Chemis, and Bukas, also existence and uniqueness results for a class of iterative differential equations with integral boundary conditions.
First of all, I would like to thank the organizers of this conference for giving me the opportunity to present my work today. My name is Chouaf. I'm a PhD student at 20 August 1955, University from Algeria. So today I'm going to give a short presentation about existence and uniqueness results for a class of iterative differential equations with integral boundary condition. The method used here is based on Schroeder fixed point theorem. The work is divided into 5 parts. In the beginning of it, I will present my problem. Next, I will convert our problem into integral equation. In the third part, I will use Schroeder fixed point theorem together with Ascoli theorem to establish the existence of at least one positive bounded solution of the problem. The uniqueness of solution will be proved in the fourth part. In the fifth part, I will show the continuous dependence of this unique solution. Finally, I draw a brief conclusion. So, the first part. In this work, we establish some suitable conditions that guarantee the existence, uniqueness, and continuous dependence of bounded solutions for the following second order iterative non-derived problem, where this term is the second iterate of x. It's worth mentioning here that iterative functional differential equations, which is a relation between a known function, its derivatives, and its iterators, is a particular type of the so-called delay differential equations with delays depending on both the time t and the state variable x. This type of equations is often used to modelize a wide range of phenomena appearing in different fields of sciences, such as physics, epidemiology, economics, biology, and other numerous areas. So let's move on now to the second part, where we will convert our problem into integral equation. Firstly, we constructed this Banach space and this convex, closed, and bounded subset of capital X. So we assume these two assumptions. And we introduce the following constants. By virtue of lemma 1, and under this condition, our problem 2.3 is equivalent this equation form, where capital A sub 1 to capital A sub 9 are given by these integrals. In the third part, from lemma 1, we defined an operator A by this expression, where beta sub 1 to beta sub 9 given by these integrals. So with help of Ascoli theorem, we can show that the pressure set is compact. So for applying Schroeder fixed point theorem to prove the existence of at least one solution of our problem, it suffices to show that the operator A is well defined, is continuous, and this inclusion. There lemma 2, we show that operator A is well defined. Under condition 2.1, 2.2, then the operator A is continuous. For phi and psi in omega, we have this inequality, which shows that the operator A is continuous. Under these two conditions, 2.1, 2.2, it's if this two inequality to 3.2, 3.3, we have this inclusion. So to prove this inclusion, it suffices to prove these two conditions. On one hand, we have a phi is not negative, and on other hand, by using condition 2.1, 2.2, and some mathematical calculations, we obtain an equality of 3.4. Furthermore, for all phi in omega and from 3.3, we arrive at 3.5. Since we have met these two of condition, we conclude that this inclusion. From theorem 1, we proved our problem has at least one solution x in omega under this condition. So by using Ardila-Ascoli theorem, we show that omega is compact. So for lemmas 2, 3, 4, all conditions of Schroeder fixed point theorem are satisfied. Therefore, the operator A has at least one fixed point on omega, which is a solution of our problem. Presently, let's move to uniqueness of the solution. Besides hypothesis of the existence theorem, we impose this additional condition to ensure the uniqueness with our problem has at most one solution in omega. So to prove the uniqueness of the solution, we used proof by contradiction. First, we assumed that phi and psi be two distinct fixed points of operator A. Then we calculated the difference between them. So we get this estimate. And by virtue of condition 4.1, we get this strict inequality, which is contradiction. Therefore, the assumption that A has the operator A has two distinct fixed points is false. That means that is has one and only one fixed point, which is the unique solution of our problem. Now we will show that the unique solution proved in the last theorem depends continuously on function f and g. So the main idea in this work consists to convert our problem into integral equation before transforming it into a fixed point problem by pursuing the following steps. First of all, we constructed an appropriate Banach space for making the iterators well defined. Second is the conversion our problem into integral equation. Afterwards, from this last one, and by using Ardila-Ascoli theorem, we succeeded in defining a continuous operator from a compact subset to itself. Finally, we conclude that all conditions of Schroeder fixed point theorem were satisfied. So if x is a fixed point of the integral operator, then x is solution of the integral equation, hence also of our problem. Here are main references. And thank you very much for your attention.
Thank you very much. It's very interesting talk, and we would like some question. Maybe somebody in Zoom would like to ask. No one, but here we have a question. Wait a moment.
I don't. Sorry, but the sound. I can't. Can you? I'm sorry, but I don't listen. You.
Okay, we have sound now. Yes, now you can listen us. Thank you, Irka. Thank you very much.
So, so there are 9 terms: beta 1, beta 2, beta 3, etc., up to the beta 9. Yes. So why some of them? And this model is theoretical one. There's no theoretical. So why some of them have plus sign and some of them have minus sign?
This model.
No.
Where you defined beta 1, beta 2, beta 3. Your constants. Previous one. Okay.
And previous one again. No,
Okay.
Or previous one.
Because
okay. Or here. Why some of them have minus sign and some of them have plus sign? If it's a theoretical model.
now this for making integral is very big. So I put beta 1 for this integral and beta 2 for this integral, and
the signs are different before beta 1, beta 2. For example, here you put this constant with the sign minus, and this constant beta 2 with sign plus. And what does it mean?
What is the reasoning?
What is the reasoning when you write down one constant with the sign minus and the next one with the sign plus?
Please, I'm a co-author in this work. Can I answer this question? I'm co-author.
No, I'm not a co-author. I'm only repeating what she said.
Can I answer this question? I'm co-author here in this work.
Okay, we'll put it here. We'll put it in chat, maybe. Okay.
We obtained this formula from the conversion of our problem into an integral equation, and from the problem at hand, there is a term plus f and minus g. For this, we have minus beta and plus beta. We obtain this by the conversion of the equation.
Yes, I understood. And my colleague, he also understood.
Conversion.
Thank you very much. Okay, we understood. It is convenient for representation of your operator. Yes? Yes, okay. Okay, thank you very much. It was the nice presentation and nice talk. Thank you once more.